So far, we've seen several ways of evaluating limits. First, we looked at limits through a numerical or a graphical approach. Then we saw that sometimes we can use direct substitution to evaluate certain limits. When direct substitution failed, you could either try factoring or the rationalizing technique to try to solve those limits. But you're going to come across certain limits, like the one I'm showing now, where you can't really do any of those approaches. You can probably do a numerical or a graphical approach, but we want to know what's the exact answer. If I try direct substitution, in the numerator I get 0, denominator I get 0, so I end up with an indeterminate form. And when it comes to trig functions, it really doesn't, or it's not too clear if we can factor anything out. So for now, we have to rely on something called the squeeze theorem. And the squeeze theorem is this. So we're going to have two conditions. The first condition is that we need to look at three functions. We need to look at h of x, f of x, and g of x. And they have to be related in a special way. G of x has to be greater than or less than f of x, and h of x has to be less than or equal to f of x. The second condition is that the limit of h of x as we approach some value and the limit of g of x as we approach some value, they have to be the same number. And over here, I'm going to show you sort of graphically what's going on. So in green, you can see that we're going to call this upper function g of x. Then in this sort of magenta color, we're going to call the lower function, we're going to call that h of x. And the function that we're interested in is this black curve here. And for whatever reason, we cannot easily find the limit. But we can find the limit of g of x and h of x as we approach sort of this c value right here. What the squeeze theorem tells me is that if the two conditions are satisfied, then the limit as x approaches that value c of f of x is going to be the exact same thing as the other two limits. You can sort of think as the curves are squeezing or sandwiching the black curve. So let's go back to the original limit that we were looking at. Limit as x approaches 0 of sine of x over x. Now, I know that g of x, if we set g of x equal to 1, that's going to be greater than sine of x divided by x. And if I set h of x equal to cosine of x, then that's going to be less than sine of x divided by x, at least when we're close to x equals 0. Now, the limit as x approaches 0 of g of x is going to be 1, because the limit of a constant is always itself. The limit as x approaches 0 of h of x, we can actually do direct substitution there. So cosine of 0, which gives me 1. Notice that those limits are equal to each other. So I can say that the limit as x approaches 0 of sine of x over x is also going to equal 1. And what the squeeze theorem allows us to do is find the limit of three special limits. And you need to memorize these limits for now. Later on in the course, we're going to find a better technique for finding these limits, but for now you need to just memorize them. So we already saw that the limit of sine of x over x as x goes to 0 is 1. You also need to know that the limit as x approaches 0 of 1 minus cosine of x divided by x, that's also going to give you 0. And then the other one, which is probably the most special of the three, the limit as x approaches 0 of this expression, 1 plus x raised to 1 over x, equals the number e. And this is how you're going to be seeing these limits. So let's take a look at an example. We want to find the limit as x goes to 0 of the following quotient, tangent of x divided by x. We can't use any of the other techniques, So we need to rely on the three special limits that you see on top. A good rule of thumb when you're dealing with trig functions is that anytime you're dealing with something other than sine and cosine, try to rewrite it in terms of sine or cosine. So tangent of x is sine of x divided by cosine of x. Let's not forget the 1 over x that we have. Let's regroup our expression so that we have sine of x over x times 1 over cosine of x. And now I have the limit of a product, which I can just take the product of the limits. So the limit as x approaches 0 of sine of x over x times the limit as x approaches 0 of 1 over cosine of x. The first limit is one of the three special limits, so that is simply going to be 1. The other, we can use direct substitution. So cosine of 0 is 1. 1 divided by 1 is 1. So we can say that the limit as x approaches 0 of tangent of x divided by x is equal to 1. Now, on the AP exam, you are, I would say 9 times out of 10, you are not going to be asked to find two other functions that are greater than or less than the function we're interested in. Instead, you're going to have to show that the conditions for the squeeze theorem are satisfied. And in class, we're going to see several problems where that's the case.